All right, in that case, I'm going to try speaking with a mask. Let me know if
I mean, you're so far that, I mean, this is a big action.
well, I have personal reasons that I like.
Okay.
Yeah, let me know if it's hard to hear, because I can speak really loud. Okay. So this is where we were yesterday. We had this physical setup where we had a 4-point correlator with 2 null integrals. And it was useful to go to this conformal frame where the null integrals are along future null infinity. And then we ended up with an integral like this, with the cross ratios parameterized in this way, where alpha 1 and alpha 3 are the parameters parameterizing these null integrals. And for the ordering that we're studying, which I probably should write here, so it's phi 4, phi 3, phi 1, phi 2. For this ordering, the correct I epsilon prescription is shown here. And the idea is that in this way of thinking about things, it's very clear how we get a d-disk. So by the way, the sum rule is then where we subtract the other ordering, where we swap 1 and 3. Okay, but I'm just going to focus on this one for now, and we'll think about the other one in a moment. So for this ordering, this is the I epsilon prescription, and in this way, it's very easy to see how you get the d-disk. What we do is we take the alpha 3 contour and we wrap it back around the singularity where 3 is light-like from 4, and the alpha 1 contour and wrap it around the singularity where 1 is light-like from 2, and this gives us discontinuities across these cuts, which leads to this double commutator. Okay, so it will be useful to write expressions in cross ratio space. So here's just the transform from alpha 1, alpha 3 space to cross ratio space. It looks like this. The only effect is that we get some non-trivial Jacobian, which is this funny square root factor in the denominator. And now we need to track the contour prescription through. And roughly the correspondence is the correspondence that you should have in mind is that alpha 3 is W and 2 minus alpha 1 is like W bar. So this is how the correspondence works in the back-to-back case. So if we take these lines to be completely back-to-back, then everything fits in a 2-dimensional plane, and you can see very clearly why one alpha becomes W and the other one becomes alpha W bar. However, for the more generic situation, the change of variables between W and W bar and alpha 1 and alpha 3 is more complicated. And in particular, it gives rise to the square root factor, and the square root factor means that there's some kind of branch cut singularity when W and W bar interact with each other. So there's some stuff happening here in the middle associated with the square root. And the correct contour prescription that comes from here is to just avoid it by having W go below the line from 0 to 1 and W bar go above. And there's a different description of this contour prescription where you imagine that W is always computed by analytically continuing away from a neighborhood of the left cut, and W bar is always computed by analytically continuing away from a neighborhood of the right cut. So that's something that you may have seen in papers about dispersive functionals, and that's the same as this contour prescription that I'm talking about here. Okay, so in these variables, it's a little harder to see how you get the d-disk, but the basic idea is pretty simple. The way you get the d-disk is by taking the W contour and wrapping it around this cut. This is the S-channel cut. And doing the same thing with the W bar contour. So you want to take both of them and go to a picture where they wrap around the S-channel cut so that you have something like this. And the double discontinuity is the same thing as disk W bar. This is equal to d-disk when acting on functions that are single valued in Euclidean space around this point, 0. Okay? And that's the case that we're interested in. We're going to be taking the d-disk of, say, a conformal block, which is a single valued Euclidean space around its OPE singularity. So this is something that you can check for yourself by just computing the sign factor that you get from disk W bar and checking that it's the same as the sign squared factor in d-disk. Okay? But, all right, so we want to do this, and it's actually not totally clear that we can do this because of this funny square root factor. So what you need to do is just plow ahead and make it work. And I leave that as an exercise. There's going to be some sort of intricate cancellation between different things that you get from the branch cuts, and in the end, you will be able to wrap things around the left cut. That's easiest to see, I think, by just imagining going back to alpha 1, alpha 3 variables, doing this manipulation, and then once you've got them wrapping around here, these are the S-channel cuts. Okay? So it's easiest to see in these variables, but it can be done in these variables. Any questions?
But how should we think of these cuts which appeared when you did the change of variable and then you change of variable? Is it because normally if you have a single valued function, you make a change of variables, it still remains single valued. So why in this case it didn't happen? Because it's apparent cuts, but somehow they are not even there. So how should we think about it?
Yeah, I think, yeah, I'm not exactly sure, but the idea is that the cuts, okay, I don't really know, but the picture I'm imagining is that you're integrating over a sheet, you have a two-dimensional sheet, and in making this change of variables, you're kind of looking at the sheet from a direction where the sheet looks folded, even though it's not. And so the square root has to do with the folding of the sheet. Yeah. Other questions?
I just wanted to make sure this, on the left picture, when you did the wrapping, that argument was based on looking at the commutator. Could
Yes.
there actually be singularities up there on the upper half plane? Because when you continue alpha 1, the phi 1 is to the left of phi 2, right? I mean, the argument you gave last time where the amplicity only works on the upper half plane, only works when phi 1 is to the right, acting directly on the vacuum.
Yeah, that's right. So the idea is that there's a region of analyticity for alpha 1 out here. And a nice way to think about it is the way Murat mentioned yesterday, which is that instead of wrapping, you can think about subtracting the contour where alpha 1 runs along the edge of the holomorphic region. Then, if you subtract that contour, then here the two contours cancel each other, because in this part of the contour, one is space-like from 2, so that they can commute. You can think of one as acting on the vacuum in this part of the contour. And here, the two contours don't cancel each other and instead give you a discontinuity.
You say for the contour up there, above the phi 1 is actually moved to the right.
Yeah, exactly. That's right. That's the meaning of this contour. So on this contour, phi 1 is acting on the vacuum. Other questions?
Can
Yeah.
I think of V as some kind of cross ratio, or is it called V for?
Oh, this one. Yes. So you can think of V as a cross ratio. And in fact, this will be important in a moment. So V is the value of the V cross ratio when alpha 3 and alpha 1 sit at these points. That's going to be important in a moment. So when alpha 3 sits here and alpha 1 sits here, then U is 0 because we're going straight to the S-channel singularity, but V is not. And if you evaluate V, you'll get this. So that'll appear in a moment. Thanks for the question. And I should say there's a different way to arrive at this integral by dispersion relations for the 4-point function. And in that case, you have 4 sets of variables, U prime, V prime, U, and V. And this comes from expanding in U, so U disappears and V is still left over. So that's another reason that we want to write this thing as V. Okay. Very good. So, okay, so now Right, like I said last time, this is half of a candidate sum rule, right? So this was evaluating one of the orderings here. We then have to subtract 1 and 3. But there are some problems with this. And there are two kinds of problems. One problem has to do with convergence of the integral, and the other problem has to do with the fact that when we subtract the other ordering, phi 1, phi 3, then we actually get an identical expression, so we get 0 equals 0. So the first thing we're going to worry about is convergence of the integral. So let's see. I'm missing a page here. Oh, it's two-sided. Ah, okay, not missing. All right. So the first thing we're going to worry about is convergence of the integral. And this will lead us to an important notion, which is the Reggie spin of a sum rule. This is a pretty central notion that will particularly play an important role when we get to holographic theories. But it's already going to be important for us now. So we have several kinds of limits we need to worry about. One kind of limit is the OPE limit, which is where, let's say, where W bar and W go to infinity, but in opposite directions. And in this picture, it means that alpha 1 and alpha 3 are going to infinity in the same direction. Okay? Then it's clear, you can see why it's an OPE limit. 1 and 3 are approaching the same point here. So there's the OPE limit, which in this picture looks like that. And there's the Reggie limit, which is where W and W bar approach infinity in the same direction. Okay? So the kernel that we have, this part of the integral doesn't really care about whether it's the Reggie or OPE limit. So we'll look at that first, and then we'll think about the 4-point function part. Okay? So we're gonna take a limit that W and W bar go to infinity with fixed ratio. This is only one of the limits that we need to care about, but it's the first one we're going to look at. So, definition. If we have a sum rule with the form of an integral over W and W bar of some kernel times the 4-point function, so we say that the sum rule has Reggie spin K if the kernel has homogeneity W to the minus 1 minus K as in this limit. Okay, so I could have also written W bar to the minus 1 minus K. We're scaling them both in the same way. Okay, and so another definition, so this is definition 1. Definition 2, which is probably more familiar to you, we say that the 4-point function grows with Reggie spin J naught if the 4-point function goes like W to the J naught minus 1 in the same limit. Okay, so now I should say I should be more precise. So in the case of the 4-point function, we know how it grows in the OPE limit, so the interesting thing is how it the usual interesting thing is how it grows in the Reggie limit. So that means there's some particular contour prescription for W and W bar. The contour prescription is to approach the Reggie limit is again you take them both above the cut here and move to infinity, or you can also take them both below the cut here and move to infinity that way. Okay, so maybe I should more properly just write Reggie limit here.
Maybe it's worth mentioning is the U-channel Reggie limit.
Oh, yeah.
Less familiar for people.
Yeah, thank you. Okay, very good. I'll say U-channel Reggie limit. Why is this the U-channel Reggie limit? Well, it comes from boosting 1 and 3 relative to each other. We're boosting 1 back and 3 forward, or vice versa. And 1, 3 is the U-channel. So that's where the terminology comes from.
In the Reggie,
Sorry, go ahead.
in the Reggie limit, do you need to subtract some identity block before you write G goes like W to the power of J minus 1?
Depends on your definition. But we're gonna have to do that. We're gonna have to subtract the identity block. Yeah, that's true. Yes.
And then how did you choose the integral contour in definition one?
In definition one, so all the kernels we're going to look at, they're going to be the same no matter what contour you choose in definition one. So I'm not going to be too precise about that in the first case. Okay. All right. Other questions? Okay. Good. So what about the case? What about the case of interest here? So so in this sum rule, you should confirm for yourself that it has k equals -1. Reduced in k equals -1. Oh, right, I forgot to write the important thing here. So there's a claim that in order for the integral to converge in the Reggie limit, we need j naught less than k. Okay? So we need j naught less than k for convergence in the Reggie limit. Okay, and the sum rule for the sum rule that we've written so far, it has k equals -1. So you should just check for yourself that at large W and W bar, this the integrand here is homogeneous of degree 0 in W and W bar, and therefore by our definition k is -1. But for a physical 4-point function, it's known that physical 4-point functions are bounded in the Reggie limit. There's a nice Cauchy-Schwarz argument that shows this. But they're bounded with Reggie spin 1 in general. Okay, so we say that 4-point functions are spin 1 bounded in the Reggie limit. So that's not good enough for convergence in our case, right? Because it's not true that 1 is less than k. So we need to do something different that increases the Reggie spin of our sum rule in order to get convergence in the Reggie limit. By the way, I should say that there's a fancy way to get this -1 that I kind of like, which is thinking about symmetries. And the idea is that the thing that we're computing is this double light transform of phi, where we're sticking the initial points in the same place. This is a product of operators with dimension. So the dimension of L delta phi is 1 minus the spin of phi, which is 1. So we're taking two operators with dimension 1 and we're formally sticking them at the same point. So that gives us something with dimension 2. Why are we sticking them at the same point? What I mean by the same point is this infinity here. So the idea is that L of phi transforms like a primary associated with the initial point where the light transform starts. And the initial point is the same because in this 10 order diagram, you may remember I mentioned last time, this whole sphere here is actually identified. It's just the point at infinity. So these contours you should think of as starting at the same point and ending at the same point. And that's what I mean by putting these two things at the same point. And the idea is that this 2 is 1 minus k. Okay, so this is using the fact that the light transform sends delta j to 1 minus delta. 1 minus j, comma 1 minus delta. We've just used that formula twice. Once to get the dimension of delta L phi, then we take a product of them, and then we do 1 minus that to get k. Okay? And this gives you the -1, and although I haven't explained it completely in detail, this is the correct way to see why the kernel that you get has k equals -1. And this method generalizes to spinning operators, for example. Okay, so we can think of this as a consequence of symmetries, just Just wanted
Sorry,
to
this was a bit too fast. Can you repeat this argument with the equations on the board?
Okay. Yeah. So the idea is that, what are we doing? So we're building a composite operator out of 1 and 3. The question is, what is the Reggie spin of that composite operator? That's the key. I claim without proof that Reggie spin of the composite operator is the same as the Reggie spin of the sum rule that you get by taking its matrix element. So then the idea is that, I'll write the formula just in general. So the idea is that what you should do is you should take delta of the light transform of the first operator plus delta of the light transform of the second operator. That gives you the dimension of the composite operator that you're creating. And then you should write this as 1 minus j of the composite operator. But this is 1 minus j1, and this is 1 minus j2, and that's equal to 1 minus j composite. So then j composite is j1 plus j2 minus 1. That's the formula that we use. So we use this formula here for how the light transform changes to quantum numbers 3 times. Here, here, and here. And putting those together, we computed the Reggie spin of the composite operator, and then that becomes the spin of the sum rule.
Sorry, that J composite is J0 or K?
This is K. This is K.
K. Because, why? K was some behavior, some kernel, why is it related to anything? So by integrating 1 and 3, we've created some composite operator. And the thing we're computing is the matrix element of that composite operator in a state created by phi 2 and phi 4. That matrix element is fixed by conformal symmetry, that controls what happens when you go to cross-racial space. But
yeah.
K, those variables are the integrated variables, not the other ones, right?
Yeah, that's right. So the integrated variables. Yeah.
So
Yeah.
I'm not giving me directly the behavior of the integral, but rather.
Yeah, I am claiming without proof, because I don't have time for the proof, that this is the correct. This then gives the correct homogeneity in the cross ratios. And I think I can explain it maybe offline, because I don't have time to go through the argument. Okay, so we need to fix this. Our sum rule isn't good in this regime, so the way to fix it is to modify the kernel. We want to multiply by something that suppresses the behavior in the Reggie limit. Confusingly, the thing we multiply is usually called a subtraction, even though we're multiplying by it, or dividing by it. Okay, so we want to stick in here some kind of function of u prime and v prime that decays in the Reggie limit. Okay? Now, there's immediately something that we should worry about, which is that whatever we stick in has to still be compatible with the contour manipulations that we're doing. Okay, so I shouldn't have erased the picture, but there's this beautiful contour manipulation that tells you that this integral can be written in terms of the d-disk. We do not want to ruin that. At least we don't want to ruin it too much. But meanwhile, we have a function that decays. And if the function decays, then it has to have a singularity somewhere at finite w and w bar. So what do we do with those singularities? Well, the worry is that the singularities could ruin this contour manipulation. Let me draw the picture again. Okay, so we have this integral over w and w bar. What can we do with the singularities? Well, if we have a branch cut or a singularity that is not located in the OPE, at these OPE points, then we get a problem, which is that when we deform the contours, we're going to pick up a contribution from this branch cut or this singularity, and that contribution is not going to be 0 on double twist operators. Because double twist operators, just those give conformal blocks that are just some generic functions, and if we're picking out values of those functions at generic positions, we're just going to get something non-zero. And so it's going to ruin this, this beautiful sine squared factor. So what's the resolution? Well, what we can do is try to put the singularities only at the S and T channel OPE points. Okay, so we have to do that. And so what is the effect of that going to be? So what we're gonna have. So first of all, let me remind you what happens with the d-disk. So the idea with the d-disk is that we get this W bar, and then in say the S channel OPE limit, we have this delta minus J minus 2 delta phi over 2 W bar to the, let's say, delta plus J minus 2 delta phi over 2. And when we take this double discontinuity, we get sine squared of pi times delta minus J minus 2 delta phi over 2 times, sort of importantly for us, minus W to the delta minus J minus 2 delta phi over 2 and minus W bar to the delta minus J minus 2 delta phi over 2. Let's say delta plus J here. Okay, so this was the way the double discontinuity worked before, and what we're going to do now is stick in a subtraction that has singularities at the S channel OPE point. So that subtraction is going to look like something like W bar to the minus minus n. Maybe I'll call it a different letter, minus m. Okay, and what does that do? Well, it has the effect of shifting delta by minus m. So it's going to give us a minus 2m here, a minus 2m here, and here as well. Okay? And you might remember from our discussion last time that this does change the structure of where the zeros are. Because this thing that we had, it has zeros at double twist locations, but only for positive n, right? These before we had zeros at 2 delta phi plus 2n plus j for all, so this is before, we had this for all n bigger than or equal to 0. And now what we're going to get is zeros at double twist locations, but only for n bigger than or equal to m. Okay? So, so this is the basic mechanism for how you get support on a finite number of double twist families. So we're preserving most of the nice things that the d-disk give us, but we have to pay this price that the functional is now non-zero on a few double twist families. There was a question?
Yeah, in terms of the OP you were saying before, is there some nice interpretation like killing an operator and getting the next one, or this?
Right, in terms of the OPE.
Or the OP of the two light array operators that we're using there.
Ah, good. Yeah, that's a great question. I don't fully know the answer to that question. What this means when we stick in this factor, we're no longer doing just the pure. We're no longer doing the light transform anymore. We're doing a modified light transform. Yeah, maybe this is useful to say. So now we're weighting the alpha 1 and alpha 3 integrals by some factor, and weighting the alpha 1 and alpha 3 integrals by a factor is something that has been considered in the literature, and it's something that people are playing with. So, for example, there was a paper by Sasha and Grisha Korchemsky where they played with weighting these integrals by exponential factors, oscillating exponential factors. And then there were earlier papers by Cassini et al. Where they said you should weight them by polynomial factors. The problem with the polynomial factors is that those integrals diverge in the Regge limit. So those aren't good. The exponential factors are nicer because they're okay in the Regge limit. But the thing that we're finding here is that another interesting thing, an important thing for this construction is to weight them by meromorphic factors. Yeah, so I don't know if there hasn't really been a systematic study of these kinds of null integrals. It might be interesting to think about. Okay, so this is the idea. So we want to add a subtraction, by which I mean multiply by something, that suppresses the Reggie limit and has singularities, but the singularities are only in the S-channel OPE limit. And by crossing symmetry, which I'll talk about in a moment, we also need to allow singularities in the T-channel OPE limit. Okay? Okay. Good. So by finding an appropriate factor with these properties, we can fix the problem of convergence in the Reggie limit. I'll just say in words. So you can see here already, there's a kind of seesaw mechanism where you can fix convergence in the Reggie limit, but you pay a price of support on double twist families. And this seesaw mechanism is kind of built into these dispersive sum rules. It seems to be a general thing having to do with like the rigidity of the space of dispersive sum rules. It's just a price you pay to suppress the Reggie limit. You're forced to get support on double twist families. And it should remind you of what happens in flat space dispersion relations, where you can change the subtraction so you can divide by more powers of S and T in the denominator. When you do that, you get a sum rule that converges faster in the large S limit, the Reggie limit. But the price you pay is that you get contributions from more things at low energies. Okay? And I can write that on the board if anyone wants more details for that. But it's basically the same kind of seesaw mechanism. And in holographic theories, it will literally be that mechanism. Okay? Okay. Good? So the other problem that I mentioned was the fact that our sum rule is just 0. And that has to do with the fact that if you take the sum rule and you plug in the S-channel conformal block decomposition, wrap the cuts around the S-channel d-disk, you get some expression in terms of a sum over S-channel blocks. If you then subtract the term where we swap 1 and 3, and you wrap those cuts around the T-channel, plug in the T-channel conformal block decomposition, you get another expression, and those expressions are identical. So you end up with 0 equals 0. And the way to fix that is, the way to not get 0 equals 0, this is bad, what we can do is choose our subtraction. So maybe what I should do here is give the subtraction a name. So we want to choose f of u prime v prime to be crossing antisymmetric. So in formulas, f of u prime v prime is minus f of v prime u prime. So what that means is if you do the same thing, it gives an extra minus sign for the T-channel contribution, and you end up with the same expression from the S and the T-channel instead of that you end up with the same expressions being added together instead of subtracted from each other. Okay. So these are our conditions that we want, and here's an example function that works. So we can just take u prime minus v prime for antisymmetry and divide by u prime v prime. Okay. So what does this do? Well, this factor is in terms of cross ratios, this is w plus w bar minus 1 over w bar 1 minus w 1 minus w bar. And so we can see that this thing goes like w to the minus 3 in the Reggie limit. And so it adds 3 units of Reggie spin to the sum. So now, instead of having k equals minus 1, k is minus 1 plus 3, which is 2. So this gives us a spin 2 sum rule. And by antisymmetry, it's non-zero. And I think this is basically the simplest thing that one can possibly write down with that's consistent with all our conditions. It has to be meromorphic. We know where the singularities have to be, and we want it to have we wanted to change the Reggie spin, but we're not looking at high spin sum rules, but just change the Reggie spin by the smallest amount that we can get away with, and it has to be crossing into symmetric. Okay, and so now we've finally arrived at our first dispersive sum rule that is actually correct. Let me write down the formula. So it's just this. We stick in this extra factor, u prime minus v prime over u prime v prime. And I'll define this to be b2v of g. Okay? The 2 is because this is a spin 2 sum. Reggie spin 2 sum. Okay. So this is one expression for b2v, and we know by construction that we can write an alternative expression in terms of an integral of the d disk. We take those contours and we wrap them around the S-channel cut. Again, we know that if we close our eyes and just push ahead, everything will work out with the square root branch cut. And so we can get an expression in terms of the d disk. It looks the same, but the contour prescription is different. So I'll just write the formula for completeness. So now we get the d disk of g. It's the S-channel d disk divided by this square root factor. And the region of integration is over the regime of cross ratios that's covered by the alpha variables, where alpha 3 is less than 0 and alpha 1 is greater than 2. So you can look in your notes for the formulas and work out the regime of W and W bar that's covered by this.
The W minus W bar disappeared?
Oh yeah, sorry, it shouldn't have disappeared. Yeah, sorry, that's yeah, that's still in there. So yeah, everything is still there, but now we have a right, and the integral is over a subregion of W and W bar on the S channel cut. So that's from minus infinity to 0. Okay? So the differences are where the integral is over and the fact that we have a d disk. Okay? And good.
Sorry, so the statement now is that this minus the same expression switching u prime and v prime is 0. Or is it not?
So no. So the statement is that this. Sorry. Yes. That's right. So if you apply this to g and then you subtract the same thing where 1 and 3 are swapped, you get 0.
Okay.
But the expression with 1 and 3 swapped is the same as the expression that we started with. Minus the 1 and 3 swapped expression is the same as the first expression. So they just combine together, and the final thing that you get is that this integral of g vanishes. Although that is not quite true, as I'll say in a moment. So the sum rule that we think we get is b2v of g is 0. And I'll leave a question mark there because there's a problem that we still haven't solved. Okay?
So I think I missed the main argument. Why were we arguing that this was 0? At the very beginning we started with 0 from crossing symmetry. Now we put some anti-crossing kernel, so I thought it was no longer a sequence.
What we did is we started with 0 is equal to an expression minus the expression with 1 and 3 swapped. Then I focused on just one of those expressions, and I explained that it could be written in terms of this contour integral of g. Just one of the expressions. But we didn't talk about the other expression. So now I claim the other expression is, in that case, was just the same. Literally the same. It gave the same sum over conformal blocks. So what we did instead is we took the crossing equation, 0 equals something minus something else, and we integrated that against the modified kernel, so that now the two terms, instead of being equal and opposite, are just equal to each other and they add together.
And the point is you're allowed to, before you do the integration, you can throw in extra terms in the measure, and those, as long as they're neuromorphic or something, it's fine.
Yeah, that's right. The claim is that this is still an integral of the crossing equation. It's just a different integral than the first one I wrote down. Yeah, Paul?
Can I not just look at that and see that G is symmetric and they're swapping U prime, B prime, and your kernel is anti-symmetric?
Exactly, yeah.
The integration range is also.
Yeah, that's right. So here you can see that's a good point. So if you squint your eyes and you don't worry about the branch cut, then you can see that this kernel here is crossing antisymmetric. So it has this structure that we like in the Bootstrap, where we act with a crossing antisymmetric object on a crossing symmetric object to get 0.
One question.
Yeah?
How did you choose this function f, and how do you ensure that it doesn't spoil the swappability of the function?
Okay, good. So swappability in this case is basically the statement that the integral converges at the endpoints. If you can control the integral at the endpoints, then all these contour manipulations are okay, and swappability follows. So that's why I've been caring so much about the endpoints of the integral, like getting the Reggie limit right, and we're about to talk about the light cone limit. So once you get those correct, then you get swappability. Was there another question?
In terms of n star, that is defined at the given vectors.
Oh yeah, good. I should write what this is. So this is a sum rule that has k equals 2 and n star equals 0. Because it has support on the first double twist family.
Well, what is this notation, the subtract V2V?
Yeah, good. So the 2 is because it's a spin 2 sum rule, and the V is because it depends on a parameter V. And the B is for Bootstrap.
So, one question.
Yeah.
So, powers of V at the denominator, they don't spoil anything of the double twist, right?
Powers of what? Of V.
V
Oh,
prime,
yes.
sorry, V
Yeah,
prime.
that's right. So these aren't the things responsible for support on the double twist families. It's the U prime. But we need them both because we wanted something crossing antisymmetric. Okay. So the last thing that we'll worry about is the light cone limit. And this is, for example, W goes to infinity with fixed W bar. Physically, well, I guess I erased the picture, but the idea is that, I'll draw it again quickly. So it's the U channel light cone limit. So the idea is that we have these null integrals like this, and we're freezing one of the integrals and we're sending the other one to its initial point. But again, these points here are all identified. This whole sphere here is actually the point at infinity. So when this operator approaches this point, it's the same as approaching this point, which we know is null from this point. Okay? Maybe it's easier to see if we approach infinity this way. So that's why it's called the light cone limit. So this is the U channel light cone limit, because 1 and 3 are becoming light from each other. In this limit, the integral that we have behaves like dw g of u prime v prime over w, and then there's some kind of dw bar integral that I'm not paying attention to yet. Okay, so just the integral over w with fixed w bar looks like this. And so we have a problem, which is that this 4-point function in the U-channel light cone limit is, at least in some locations, dominated by the unit operator in the U-channel. What do I mean by some locations? I mean locations where the 1,3 OPE is valid. Okay, so if you're in a configuration where the 1,3 OPE is valid, then you go to the U-channel light cone limit, and it's dominated by the unit operator, which means that this thing here, the 4-point function, behaves like 1 in our conventions, which is what the U-channel unit operator looks like. And so we get an integral dw over w, which diverges. So what we'd like to do instead is replace. We want to subtract off the U-channel identity. So we want to replace G with G minus 1, okay, where this is the U-channel identity. When we do that, as long as this thing is little o of w, that is, as long as this thing, little o of 1 over w, as long as this thing goes to 0, as w goes to infinity, then the integral converges. Okay? So, I'm using kind of squirrely language here, because this is indeed true in the OPE regime that I mentioned, where you can use the OPE to compute the U-channel light cone limit. But this integral also includes a regime called the light cone limit on the second sheet. Sometimes it's called that in the literature. It's a regime where you cannot, at least we don't know for certain that you can apply the light cone OPE to determine the behavior of the correlator. And so we're going to assume that our function g satisfies this condition. Okay?
Should that be 1 over w to any positive power?
Yeah. Sorry, I shouldn't have said 1 over w. I should have just said little o of 1. That's the notation that I meant. As w goes to infinity. Yeah, little o of 1. So that means it's something that goes to 0 as w goes to infinity. Yeah, and it doesn't matter how fast it goes to 0, it just has to go to 0. We're going to assume that this is the case in order for these to be valid. If you like, these sum rules are valid when acting on a CFT 4-point function that satisfies this property. But there aren't very many, there aren't really good rigorous bounds on the behavior of the 4-point function in the light cone limit on the second sheet. So I want to mention this as an important open problem, getting a handle on the behavior of these 4-point functions. There are conjectures about how the 4-point function behaves on the in this light cone limit on the second sheet. There's a conjecture due to Hartman et al. That this thing actually goes like 1 over w to the twist of the lightest twist operator, the lowest twist non-unit operator in the OPE. So this would definitely be sufficient. I guess this should be over 2. That would definitely be sufficient for what we want, if that conjecture is correct, but it's still a conjecture.
So the region where this is happening is just when one of the points is like as time like separated with respect to the operators that are not integrated over.
Yeah, that's exactly right. Yeah, that's right. So the problem occurs when this point is time like from both of 2. So sorry for all the points in the crappy notation, but let's say 1 is going down here. The problem is when 3 is time like from 2 and 4. That's exactly right. So when 3 is space like from either 2 or 4, then that's where you can use the OPE, and you're in good shape. And we know rigorously that this condition is true. But in this regime where 3 is time like, that's not the case anymore. That's the light cone limit on the second sheet. Okay. Very good. So, okay. So what does this mean? Well, assuming a 4-point function has this behavior, that g minus 1 goes to 0 on the second sheet, as well as on the first sheet, in the light cone limit, then our correct sum rule is that B2V of g minus 1 is 0. In this case, we've looked at all the limits we need to look at to establish that the integral converges. And so this is the sum rule that we get. And so now we can write this as a sum over conformal blocks. And the way that works is that you insert the conformal block, you insert the conformal block expansion of G, the S-channel block expansion of G, and the S-channel block expansion of 1, which is a sum over double twist operators in the S-channel. Okay? These are with the coefficients of mean field theory. And then you do the contour deformation, and you use the formula in terms of the disk. When you do that, you get a contribution from one of the mean field theory operators. And you also get a contribution from the physical operators that were there already. The contribution from the physical operators gives you B2V applied to a conformal block. And the contribution from the mean field theory operator gives you a -1. So the sum rule that we get, just to write it again, is a sum over delta J of P delta J, B2V of G delta J, S, is equal to 1, not 0.
Sorry, just to make sure, this one is this n star equals 0 operator that... No.
Yeah, that's right. It's one of the n star equals 0 operators. It's
Okay.
I think it's just the lowest one. It's the lowest scalar operator in mean field theory.
Thanks.
That ends up giving it.
So your question?
Yeah.
So is the original limit a subset or a special case of your light tone limit on the second sheet because you can send both 1 and 3 to?
Yeah, that's right. It's next to the light cone limit. It's related to the light cone limit. So yeah, there's an overlapping regime where you start at the light cone limit and then you send the other operator to infinity. And alternatively, you can start in the Reggie limit and make the ratio between W and W bar very large. And those limits should overlap with each other.
So why can't we fix the original limit by subtraction, but the light cone limit is more difficult, it seems. You have to do G minus 1, but you don't have to do this for the original limit.
It's because in the Reggie limit, the only thing I analyzed was the radial part of the integral, where you're moving in the radial direction in W bar space. It didn't talk about the angular part. And the light cone limit will turn out to bite you if you then think about the angular part. Yeah, great question. Other question? Okay. Okay, so there's an alternative way of arriving at dispersive sum rules that I want to talk about because it will also give us some important and useful formulas when we try to actually apply these things, which is via Mellon space. Okay, so the idea of dispersive functionals in Mellon space is conceptually perhaps a lot simpler than this. It's just a dispersion relation in Mellon space. Okay, so it's just the Cauchy integral formula in Mellon space. So let's look at a Mellon amplitude. We have M of S and T. And we're going to be interested in fixed U dispersion relations. So that means that I should solve for T in terms of S and U. So this is for delta phi minus S minus U. And this is a function that has poles in the S-plane that are controlled by the OPE. So the poles, so the squiggly line means that I'm now writing the structure of the poles of this function. They're a sum over operators in the theory, P delta J, and then for each operator, we get poles at an infinite set of locations labeled by an integer m. The residue of the pole is these so-called Mach polynomials, Q delta J m of U. And then we get a pole in both the S channel and the T channel. So S minus tau minus 2m, where tau is delta minus J. That's the S channel pole, and there's also a T channel pole for delta phi minus S minus U minus tau minus 2m.
Sorry, I think I missed the punchline of this beautiful formula. So
Yeah.
If we start with crossing and apply any functional, we get a sum rule, right? Or no? The point is this one. What's special is the one instead of a 0.
Yeah, that's right. So the idea is that we have this functional b2b, which is a certain contour integral, but we have to apply it to g minus 1. And that gives us 0. And if you then try to write it in terms of conformal blocks, you get this expression. So another way to say it is that b2b by itself is not swappable when acting on a physical 4-point function. It's only swappable when acting on g minus 1. So
this one, should I think that we are subtracting into theory 4-point function from the full 4-point function, or is it just subtraction down at the level of g? Like for example, could I subtract instead of 1 any other function which behaves like 1 in that limit?
Yeah, you should be able to subtract any other function which behaves like 1 in that limit. If you choose another function, then I think you should end up with the same sum rule, but you might have to work much harder to get it, because you'll have to sum up many more contributions to get the thing that on the right-hand side. So for example, you could subtract two different physical 4-point functions from 2 different theories, but with the same delta phi. That would work.
Okay.
No, but then it would not be. Then you would get the left-hand side of one theory equal to the left-hand side of another.
That's right. You would get that the sum over conformal blocks of you would get this sum in one theory is equal to the same sum in the other theory, but you wouldn't know that both were equal to 1.
Doesn't seem like the right
Unless you knew the theory, and for example, we know mean field theory, so you could evaluate it in that case. Other questions?
But it is not the same as what people do in the usual Bootstrap, where you separate the identity and then you get whatever the functional gives on the identity plus the rest. This is different.
Yeah, it's not the same. Yeah. The identity block is still here in this sum. There's still a term for 0, 0. This is different. It's a different contribution.
It's a new channel.
So what if you start with a 4-point function of distinct operators? Like
distinct operators.
Yeah.
Yeah.
Get rid of the identity in this way.
It all depends on this behavior, exactly what you need to subtract. So yeah, if you apply this to a 4-point function where the U-channel identity is not present, then you don't need this subtraction.
But do you expect? Because then you get something to 0. So you expect that there won't be positivity or what?
No. Well, I haven't even talked about positivity yet. You get a valid sum rule. I think it should work.
Okay.
Okay. Okay. All right. So back to Malin space. What I'm going to do is describe a construction for you that gives a spin-2 sum rule with support on the first double twist family. The surprise, which I'll give you a preview of, is that it turns out to be the same as B2B. So it's some evidence for the rigidity of the space of dispersive functionals, that we use a completely different construction and we end up with the same function. But as I say, the formulas we get will actually be useful for us. Okay, so we have these poles in the Mellin variable s, and this is a so-called map polynomial, and the important thing for us is that this Q contains the all-important sine squared factor that we care about. So in the Mellin variables, if we get something that just picks up values of Q at different points, then we'll immediately get a sum rule with this sine squared factor in it. Okay. All right. So these are the poles, and then the other thing we need is Reggie boundedness, and there's a claim that this thing goes like O of s as s goes to infinity. So okay. So to get a sum rule with Reggie spin, so this O of S is Reggie spin, is growth with Reggie spin 1 in Mellon language. And to get a sum rule, a spin 2 sum rule, we need to divide by 3 powers of S. Good. So we need to divide by 3 powers of S. We need to put the singularities somewhere when we do that, and it's natural to put the singularities again at these double twist locations. That gives the simplest sum rule. And so the sum rule that we're going to look at is a contour integral over S, and this factor of 2u up front is just for future convenience. Doesn't really do anything important. We'll take a contour integral of m of S and t divided by these powers of S, but we're going to put the powers of S at locations that lead to a nice sum rule. And this is again at fixed u, so this is evaluated at t is 4 delta phi minus S minus u. Good. So the idea of where these subtractions are is that we're putting them at places where there are zeros coming from the q factors, so that if there weren't zeros, we would get a sum rule that makes reference to the Mellon amplitude at the point where the subtractions exist. That is not an interesting object for us. We don't want that object to appear in our sum rule, so that's the reasoning for where we put the poles. Okay, so this is the contour integral that we'll look at, and if you use the locations of the poles that I wrote up here, we immediately get a sum rule. 0 is a sum over p over delta j, p delta j, of the contribution from all of these poles. So we get a sum from n equals 0 to infinity, 2u q delta j m of u over these factors from the subtraction, which I'll write like this: tau plus 2m minus 2 delta phi.
So what's the contour integration?
Good. Oh yeah, I should have said this is a contour integral around infinity. So you start with a contour integral around infinity because by this Reggie boundedness, the integral is 0. You bring the contour inside and pick up the contribution from all the poles. Yeah, thanks. I should have said that.
What is the domain of convergence in S and T?
What is the domain of convergence? Okay, good. So that's a possibly subtle question to which I'll defer to the experts in the room.
Well, we proved part of it, but all of S and T complex plane, we cannot prove. There is some conjecture. If you go to both negative S and T, we don't really know if it's an analytic function with just this pole, non-totality. I suppose that's related to your assumption there, right?
Yeah, that's right. So this is gonna pop out. This light cone limit thing is gonna pop out in this. We'll see its significance in this analysis in a moment. In fact, the problem is it's not gonna pop out. We'll see. So maybe we can let me defer this discussion for just a moment. So that's a great question. Just sort of the conceptual status of this. And let me just finish writing the formula. Okay, and I'm going to define this stuff here as B2 hat, comma, gamma of G delta J. That's a gamma. Where gamma is just 2 delta phi minus u. Okay, so we started with a sum rule that was parameterized by u. We could pick u to be whatever we want within reason, and do this contour integral. And now I'm just going to label it by gamma. And it was just simply related to u in this way. Okay, good. So we have this sum rule, and it looks very much like So at least the way I've written it, it looks suggestively like some kind of functional b2 hat gamma applied to a conformal block. So this is somehow our dispersive sum. And the nice thing about this is that it manifestly possesses double zeros on double twist families above the first one, because of the double zeros inside the two functions. Okay? And the reason it doesn't have a double zero on the first family has to do with these attraction factors. You can see that they've produced poles that cancel the zero. Okay? So this is this is much easier than the first thing I discussed. Much simpler looking, and it also leads to a nice explicit formula for the value of the functional. So we can ask, well, wait a minute. So before we had a rather constrained construction where we were led to a spin-2 sum rule with support on the first double twist family, and now we have another construction. And what's the relation between them? It turns out that one is just the Mellin transform of the other. So I claim that B2 gamma hat is just equal to some gamma functions times the integral from 0 to infinity dv over b to the delta phi minus gamma over 2 b2b. And you can write the inverse transform to this as well, if you like. You can write b2b in terms of b2 gamma. Okay, so this is a claim. This claim should this claim should make you immediately worry a little bit about this term, because this is supposed to be the true sum rule satisfied by B2b, and so we can then try to Mellin transform this sum rule, and we get a sum rule for B2 gamma. But what about this term? Okay, so the 1 is really there in B2b. What happens when we Mellin transform it? Well, formally we get 0 because we get delta of gamma from here, and then there's a 1 over gamma of gamma in the denominator, so we get a 0 times the delta function. But I think probably more appropriately we should think of it as some kind of distribution in the gamma variable that is a non-zero distribution, because it's definitely non-zero over here. So I think this is a reflection of the subtlety of working in Mellin space. It's probably related to questions about the regime of convergence of the Mellin transform to get M of S and T. These are somewhat subtle questions, and ultimately to answer them, I think you have to think very carefully about the position space correlator. And it would be really interesting to trace all the logic through and understand the distribution at gamma equals 0 more directly.
And how clear do you think it is that it's not 0, that the right interpretation isn't just 0?
Well, this is a sum rule that one can test.
Yeah.
And it's a true sum rule.
Yeah.
And so that means that there exists. So you can think of this as the Mellin sum rule smeared against a test function that turns b hat into b. So that means that it should be possible to smear the Mellin sum rule against test functions. Maybe we shouldn't call them test functions. Against some functions, should be possible to smear them against functions such that the right hand side is non-zero. So that means that in the Mellin language, we need to stick a non-trivial distribution over here.
Or perhaps alternatively, like this Mellin version is only valid in some range of gamma.
Yeah, that's right. That's right. So this suggests that the Mellin version is valid for gamma not 0.
What we've been thinking about is that we consider not the correlation function, but the correlation function subtracted by the identity and operated as a small list, so this column does not appear. We don't really need to think in terms of distribution.
Let's see. You're saying you should think of this as the Mellin amplitude for the 4-point function minus the identity.
Yeah. or more subtraction.
Okay.
By the way, just another comment. So here we were thinking about the convergence of that sum within bounded space, so we understand exactly where it converges. There is just an issue which is we make assumptions about the novaticity of the Melvin amplitude, so we're saying that the Melvin amplitude is monomorphic. This we did not really prove, so we needed to, when we were studying this, we need to assume that UP converges in a region where we don't know where it converges, so that was the only assumption. I'm pretty sure that you guys make the same assumption. As you said, you guys make the same assumption.
Yeah, it's likely the same assumption, yeah.
Yeah, convergence, we understand. I can understand.
Okay. Very good. So okay. So this is the big claim. So let me just say how you prove the claim.
Sorry. Does the net amplitude already subtract the identity? Because the identity should be some delta functions if you write it in the Mann space.
Yeah, that's what he was saying. That they usually think about subtracting the identity. Okay. So yeah, I'm not claiming it's not possible to do the analysis correctly in this language. It's if you like, it's a challenge. Please do the analysis properly in this language for us and show us how it works. Okay. So so this is a claim. The idea for the proof of this is that you can write a formula for the S-channel poles in the Mellin amplitude as an integral not of the 4-point function but of the d-disk of the 4-point function.
David, you started 5 minutes late.
Yeah.
But okay, I don't know.
And now I've gone 15 minutes over, so I'm 10 minutes over, right? And last time I was allowed to go 15 minutes over, so I have
So if you go 15 minutes over, you have like 2 minutes. So.
2 minutes. Okay, yeah, that's fine. That's fine. Okay. Anyway, there's a formula here that you can write that importantly is an integral of not the 4-point function itself, but the d-disk of the 4-point function. And the price you pay for putting the d-disk in here is that you have to divide by these ubiquitous sine squared factors, but now as a function of this Mellin variable. And the idea is that this is an alternative formula that has the same S-channel poles because the sine squared factor in the denominator cancels the sine squared factor coming from the d-disk, and you get the poles have the same residues. And the nice thing about plugging in this version is that this sine squared factor in the denominator, when you then go to do the integral over s, behaves much more nicely. And you can actually do the integral over s. So you take this formula, you plug it into this sum rule, you do the integral over s, and you end up with an integral of the d-disk times a function of u prime and v prime. And magically, that function of u prime and v prime is exactly this square root thing that we had before. Okay, so so that's the argument. So you land on the formula for V2V written in terms of the integral of d-disk against this square root factor. So it turns out that these sum rules are essentially the same, and we're going to use that. We're going to use that shortly. Okay. So I guess I should stop there. Are there any more questions?
If not, let's thank you.